Today, we're going to talk about thermodynamics. This is probably the last step of the chain of asking when you learn a new topic, what are the things you should ask. So remember, in part 2, this is about thermophysics. Just a recap. Chapter 4, we start with first the intro to basically what is heat. 5 and 6, we look at expansions, ideal gas, and the kinetic theory. And now we're leading to thermodynamics. So remember, usually when you learn any new subject, not only physics, but if you take a biology class or a chemistry class or whatever, you want to ask first, what is it? What does it do? And why do we care? That will help you not get lost in the forest of technical details and learning definitions after definitions. In biology, there's lots of definitions or facts and concepts. In physics, people don't realize there's a lot of definitions for some reason, but there is. Any subjects have to have definitions in that subject. So it's easy to get lost in those technical details. In physics, the extra thing is it's easy to get lost in equations as well as we go deep into proofs or maybe some derivations or some conceptual arguments. So this is the best way to study, having that linear. So remember that we realize heat is energy, and objects have internal energy. So when the internal energy of one object goes to the internal energy of the other object, the amount that goes from A to B is called heat, that amount, that transfer. And how do we measure it? We macroscopically, in daily life, we measure it by temperature using a thermometer. And okay, so now we know heat gets transferred. What does it do? We talked about, well, first of all, it will increase the temperature because that's a direct measure of its internal energy. So if you transfer some heat to something, the internal energy increases. So you directly measure that from temperature. Actually, this should be a little bit part of what is it, because that's the microscopic view. And we show that temperature is directly related to the kinetic energy, or otherwise known as speed, because kinetic energy is essentially speed, well, times mass, the speed squared times mass, and then you divide by 2, right? Half mv squared. But roughly speaking, essentially kinetic energy is its speed, right? It's a reflection of its speed. So the temperature is basically a reflection of each particle's speed, but not each particle, but the average speed, right? And also not average in the normal sense, as we see in the derivation, is the average of squares of the speed, and then you square root, right? It's a little bit more tricky. I've had a document elaborating a little bit on what's root mean square on Canvas, so it's under supplementary notes under the lecture slides that you normally see. So you can check that out a little if you want to gain a better intuition and concept understanding of what is RMS. Okay, so temperature increases. The next thing is it will expand. And essentially this takes care of solid and liquid, basically how this would react to heat. And here is basically how gas would react to heat, right? So what does heat do to solid and liquid is basically summarized in this chapter. Basically, the only thing it does is it expands the solid and liquid. It doesn't change the pressure much. But for gas, it does change the volume and the pressure equally when temperature increases. So PVT are our primary macroscopic variables, right? And that this chapter ties. This should probably belong to up here. What is it part, right? Okay, now what do we care? We care a lot because this is where we take this and basically kickstart us into the modern world, the whole industrial revolution. We basically, in layman language, for the first time, we're able to make machines, okay, or modern machines at least. Okay, so today basically we'll cover thermodynamics, and just to give you an outline, what are the things, we'll kickstart immediately with the first law of thermodynamics. And then I'll introduce 4 thermodynamic processes that we can use to make machines. And then the idea of thermodynamic cycles, we'll get to what that is in a second. Then once you know what a cycle is, then we'll see how do thermodynamic engines work. Okay, so thermodynamic engines is basically the general term of everything that goes from the car engine. So today, by the end of today, you'll basically know the principle of how a car engine works. More technically, it's called an internal combustion engine. It's that tank of what's going on over there. How does it take the gas that you get from the gas station into the car moving, into it actually doing work for you? Heat pumps, and surprisingly, believe it or not, refrigerators will be part of our topic today. Okay, so that's the plan. All right, so one more comment is this chapter is quite different in terms of style of how we analyze the physics of things. The physics is the same, but the way we approach it and think about it is a little bit different from either everything we've done before in fluids or 3A, and also later on, the next couple of weeks. It's a kind of an odd man out in thermodynamics. In most cases, if you think back in how we analyze fluid problems, if I ask you what's the world's longest straw you can make, right? And then usually what we want to train you to, the method of thinking like a physicist is you zoom in and ignore a lot of extraneous factors. Zoom in into the primary factor. It's the weight of that fluid, because the higher it gets, right? The higher it gets, you have more fluid on the straw, so it's heavier. So now you need to somehow suck that up. How do you suck that up? You need a pressure difference, right? You need a pressure gradient. So the philosophy is you zoom into the object of interest, and then you draw a free body diagram. You analyze it in a very individuality, very zoomed in way. But here in this chapter is one of the rare chapters in physics where we actually zoom out. So I describe it like, imagine playing golf all your life with your dominant hand, with the right hand, for example, and then suddenly I tell you today to use your left hand. At first, it feels a little bit weird the way we approach this physical problem, but it is interesting nonetheless. It's a new skill that you can learn, and the way I think of it is almost like switching hands in golf. It's probably you're never going to do that again in your life, but it's cool while it lasts. Okay, so thermodynamics, what is this? Dynamics is the study of movement. Thermo is the study of heat. So what does that mean? So putting that together is the study of turning heat into, you got it, movement, or let's call it useful work. So we want these engines to do work for us, right? And occasionally we also it's also the study, it goes both ways. You can take work and change it into heat. Usually you want the heat to do work for us. Why would you want to do it the other way? Well, for example, if you are living in some northern states or some place where it's very cold, you really want to rather do some work and turn your house into a little bit warmer heat tank, right? So sometimes you want engines that turn work into heat, and a lot of times you want to turn them from heat to work, right? So to focus on from heat to work first, we'll use that as a guideline. The reference chapters, as usual, it's 19.6 to 9. And also, as I said, part 2 thermophysics is actually quite a vast topic. There will actually be a small extra topic on the second law, entropy, and what's entropy. As you look at my timetable, that gets leaked into the next week, the first lecture of next week. That will not be tested. That will not be covered, although it's part of thermophysics as a whole. Right? This segment, this part of the course, but it's not going to be included in the test 2, if anyone's wondering. Okay. Cool. So. Probably the first thing you need to remember is what is work. So how many of you know that from 3A? Right. So let's do a quick recall before you freak out. So work done is the concept. Now, we sometimes say work, but work done is the proper term. Work itself is not well defined. You cannot say something has work. You can only say something has work done on it. And also, just like forces, it has to be on something, by something. Let me emphasize this by changing the color. Every time you think of work, every time the word work pop up, I encourage you to immediately put a little alert in your head and ask yourself, what is it on? What is it by? Right? Train yourself to think the fine prints of these things. All right, very simply, if you have a box and you want to do work on it, what it does is you move it, then you're doing work. That's all work done is. You move it from some initial state to some final state. Let's say you push it. And what you do is you apply some external force on it, and it's very roughly speaking, the work is the external force times the distance. So if you move it by more distance, you do more work, and the more force you apply it to achieve that distance, you do more work. Now, I will always use a delta in front of the work, just like I always use a delta in front of the Q. Okay, and as you will slowly see, that will be justified as well. Okay. So what the way we say this is we say we have done work on the object. This is the grammar of how you should speak of work. Okay, so you see, work is always associated with done, right? It's always work done come together. And look, it's what is it on? What is it by? It's on the object, and what is it by? It's by us. We are supplying that source of force, right? Or another grammar to read it is work is being done on the object. That's not a complete sentence. On the object by what? By us. Okay. So no matter how you phrase your grammar, work done is always come together, right? And it's always on something, by something. Okay. So both ways is the correct way to speak of work. All right, how does this relate to us? We want to turn what? We want to turn heat into work. How can we do that? Basically, the idea is I don't want to push the box. I want something else to do it for me. I want heat to do it for me. How can we do that? There's an easy way. So this is basically every single machines, or not, I wouldn't go that far, but or I would say most mechanical machines. I have to insert the word mechanical because your iPhone doesn't work with heat. It works with electricity, which is the next topic, right? Electricity is going into the digital side of things, but mechanical machines work in this basic principle, okay? So once you understand this basic principle, a car, a refrigerator, and a lot of the heat pumps are all based in the same principle. So imagine you have a box of gas, okay? You have a box of gas, now you heat it up. Okay, it's a Bunsen burner or something. Then what you have over here is called a piston. You put a piston over here. So a piston is a frictionless valve. Okay, so it's free to move. That's free to move. Okay, so when you heat it up, as we learn, most of the time things will expand, including gas, right? So if it expands, it will move from A to B, right? The piston will move from here to here. And as a result, now, if you are clever, you can connect the other end to push the box, and now the box will have moved from the same distance the piston has moved. And now look, I have moved the box from A to B without me touching it. I just heat up the gas. This is, in one sentence, we can almost end the lecture now, is how heat engines work, right? Now you replace the human being with the expansion of gas. Now you understand why we study ideal gas, why we study expansion. And first we need to understand what heat is in order to able to analyze this properly, all right? Another way is, you can take this, right? The piston will push. Now, connect this to a wheel with a fulcrum over there, like some hinges, right? So if the gas expands, it will push this, and you have an axis over here, a rotational axial axis over there. So if the gas expands, right, so this will start turning, and then it will turn over here, and when it reaches this point, you'll need the piston will probably here, but now you need the gas to contract for it to go back to its original state. Gas will need to contract, right? So now, if you were able to put a candle over here, and then you move it out of the frame so that it cools down, and then it contracts, and then you move it back into the frame and move it in and out at the same time like this, you can drive a wheel to work. This is how cars work. This is how a steam engine works. Well, actually, close enough. Steam engines are train engines are a little bit more complicated. It uses the gas actually to push the wheels as well. But this is certainly how your car works. And it's basically taking a candle and bringing it in and out of the gas tank. And that's why you need fuel. That's why you need gas, because you need to burn something. That's why it's called internal combustion engines. All right, cool. Now, this is called a thermodynamic process. Okay, it's the process of how you make it go from A to B. Okay, because how much do you expand the volume? How much do you expand the pressure? Do you keep the pressure constant and purely expand the volume? Is that the most efficient way? Turns out no. Turns out it's a combination. But on the other hand, if you remember, gas is more complicated, right? Because P and V can both vary. So if you put the candle there and then only the pressure increases and the volume does not, that's technically, I guess, that's a thermodynamic process, but it's a very useless one that it's not doing any work there, right? Because what you really want is to expand the volume so you can push something else. But what's interesting is it's actually not the most efficient way. We will see by the end of today, once we put in the equations, and then you'll find out, interestingly, it's not the most efficient way when you 100% transform all the heat into volume expansion. You actually want some pressure change and some volume change. And the bottom example is called the thermodynamic cycle, the word I introduced earlier, right, in the outline. Right? It's a cycle. It's basically a combination. If you put a few process together, and then the initial state is equals to the final state, or the final state equals to the initial state, so it can actually keep going. Not just a process. You see the difference. Process means it goes once, and a cycle means there's some way of bringing it back and then repeat and rinse and repeat. Okay. So work is force times distance, but for us, because we're dealing with gases, it is actually much better to transform into the variables we are interested in. All right, so we're interested in PV and T. So it's good to able to express the work in terms of PV and T. But first, let's recap what is the formal definition of work done, in case you, I'm sure all of you know this extremely well in 3A, right? But just in case you don't, we'll just apply this here. So on something by something, work done, right? It's the product, for now, actually the more correct way is a dot product, but we don't have to worry about that for now. Next week, we'll actually come back to that because it is important for electricity. But for now, we will keep it simple. It's the dot product of, or the product of force and displacement. So the force, we use the symbol F, of course, and displacement is delta X. Okay, delta X means X2 or X final minus X initial, XB minus XA, X2 minus X1, whatever symbol you like to use. All right. For now, we will keep everything in one dimension, like I say, only if it's more than one dimension. Next week, we'll have to worry about the dot product. So for now, it's just remember that. So in equation form, not equilibrium, sorry, equation. If it's in one dimension, I'll give you two definitions, and you need to use it appropriately. If it's in one dimension and the force is constant with respect to what? When someone say constant, always ask with respect to what? With respect to through the delta X, through the displacement. Okay, so throughout the journey of delta X, when you move something, if F is constant, then the definition is very simple. The work done from initial to final, actually this is so, the labels is so important. I'm going to change the color, but let me write the rest first. And I really encourage you to put in a label, something like this. Now, some of you might be concerned about exams. Remember, while the teaching part of things, I will concern less about exams, but once you understand it, we'll talk about exams. But I'll make a quick comment about that. Should you label things in exam? The quick answer is the first step, yes. And then feel free to drop it everything else because you become lazy. For me personally, I drop it gradually. The reason for that is in the first step, you need to tell people what is the variable you're using, because you might use a different variable from another student or another book or another TA. The TA might use a different variable. So you need to be able to, if you label down a diagram, that's the best way to address it. And a little labels, delta W of an ice cube or something like that, that will tell whoever. And then you can, because it's a pain to write it every time, right? That would be too inefficient. So you drop it gradually. That's me, but if you want, you can drop it right away, because now it's just following the math and it's clear where that comes from. If in the middle, I find out, oh, what is M again? Is it the mass of the boat or mass of the water? And then I just have to follow up the steps. If you present your steps clearly, they should be traceable. Traceability is a very important thing in presenting solutions. Now, if it's one dimension and the force is not constant through delta X, right? If it keeps changing, then you need the more sophisticated form like this. It's the integral form of F times dx. So not F delta X, but F dx, and the integral, think of that as adding up all the F dx's. Okay, so note, this is basically, of course, the first case is a special case of the second case. Because if F is constant, then you can pull it out of the integral. And this is basically integrating 1 dx, right? Integrating 1, it gives you x. And now you need to substitute. It's a definite integral, so you substitute xf minus xi. And what's that? It's f dx, x delta x, sorry. So you see the first case is recovered. So you see the second case is more general, but if you know the force is constant, directly use the first case. In this class, in this lecture actually, both will happen. You can sometimes, sometimes the force is not constant, sometimes it is, okay? And here's a tip. So 2 tips when you working with this, working with work. Tip number 1 is in one dimension, especially, worry about the magnitude and direction separately. Okay, this is what I would recommend. This is how I solve things. So always, when you solve the magnitude, just do the F delta X. Okay, so when you calculate that, just do from I to F. You see now, slowly I start dropping things. I drop the arrow because it's clear. It's going from initial to final. Once you know, so this is how I do my exams as well. So just do finals minus initial. Don't worry about which one minus which one. Usually just do final minus initial. And then think about the direction. Should this be positive or negative, right? So which way should it be? Then the idea is this. If the force is pushing in the same way it is moving, then it is positive. If you push it this way and it moves the other way, then it is negative. Okay. Basically, this is someone doing work on the object, and then this is the object basically being done work on. Okay, so someone else is doing work to push it the other way, and it is resisting it. So there's a negative sign. It'll be more clear when we look at actual examples. And I also want to comment on the delta part of it is this. As you can see, work is always some sort of difference. Look at the symmetry over here. If I have delta on this side, this delta on this side. A lot of textbooks don't write the delta. I'll tell you why. It's because whenever you talk about work done, as I emphasized in the first slide, it's always a change. If you can never talk about the work of something, period. You cannot talk about the work of something without a change. It has to be work of something. It has to change from state A to state B, and then you look at the difference in the energy of that is produced between that. As a result, a lot of books would say, well, since just having W itself does not make sense, every time I write W, I just mean delta W. Okay, that's why they drop the delta. However, it's going to get confusing later because for E, energy, E and delta E is different. W and delta W is in principle different, but this does not exist in physics. You cannot talk about this. So people are lazy and use just W to mean this. But now it causes a confusion when we look at the first law of thermodynamics. If anyone have seen that before, you have E and W at the same time. Now, when you write E, you might wonder, wait, does that mean delta E or E? It will cause a lot of confusion there. That's reason number two. Reason number one was the symmetry of these. This many other reasons why this is much more preferable and not being lazy. Just take the 0.1 seconds to just put in a delta over there. Trust me, it ultimately helps you. Okay, so let's address. This is our first law of thermodynamics. Now that you know what work done is. So what this says is it's the total change in internal energy of the system. Okay, these are the fine prints of the system. We use delta E internal. This delta is definitely important, cannot be dropped. It's equals to the total heat added to the system. I'll emphasize two. And I use delta Q. This delta, yes, you can drop, but I like to keep for this reason that I just explained, plus the total work done on the system. Okay. So in equation form, this is how it reads. So any change in internal energy is any heat you add to the system plus any work done on the system. Okay. So as you can see, some books would just write delta E equals to Q plus W like that. But now you see this reflects what we're talking about in the word form of the law. The equation reflects the words. This one, people just say, well, Q doesn't really make any sense unless you talk about delta Q, so that's not what works, right? The delta. That's the reason why they drop. Your textbook, and I think most books actually do this, but I think this will help your understanding a lot. Now, also, speaking of books, the community is kind of 50-50 split between this. Some books write first law as the total change in internal energy is equals to the heat added to the system. People agree on this, but then they say minus. Some books will choose to do minus instead of plus the total work done by the system. Okay, so that's why you see why I emphasize the subscripts on and by. So in their form, I forgot what our textbooks did. I think it's actually the latter, which kind of bugs me sometimes. But honestly, it is 50-50 in the community. So they write it like this. They're actually the same thing, because think about what it really means. This is essentially a statement of what? Statement of conservation of energy. It's basically saying energy is conserved in this particular way, in this special way, that if you add heat to the system, it will increase the internal energy. Sure, we know that. if you do work on the system, it will also increase the kinetic internal energy. So what is doing work on the system? Well, remember, work is moving things with a distance. So if you remember that piston, you squeeze it in, you will increase the internal energy. So that's why I like the plus version more personally, because you do something to the system and you do something to the system, it'll increase its energy. Now this one says if you do something to the system, so you add heat, it'll increase it. And if the system do work, so if there's work done by the system, this will decrease the internal energy. Again, it makes sense, right? It's up to you which one you like to use. So without the subscripts, textbooks may write things like this. So you see all this. Personally, as you can tell, this is the most clear what things mean. Okay. So that's a conservation of energy. It's telling the two things we can do to a system. We can add heat and we can do work. Sometimes, actually, there's some reason for just some excuse for this as well, because we're interested in how much work the system does. So we're interested in actually the work done by the system. So you kind of want that in here. But maybe I'll make a comment here is you learn that the work done on something is negative of the work done by something. Okay. Just kind of obvious. If you do work on it, then if one is positive, the other is negative. Okay. So what are the ways we can construct engines? So these are the 4 common ways, 4 common thermodynamic processes. Okay. And these are this is probably at the heart of this chapter that you need to learn in the problem solving side of things. There's one called isothermal process. What does isothermal mean? Iso means the same, thermal temperature. So that means the temperature is kept constant, meaning temperature from the process moving it from the piston from A to B, moving the piston from A to B, the temperature doesn't change. Okay, so that's one way to do things. Another way is isobaric process. Isobaric, bar is it's an older fashioned word for pressure. So this means the pressure doesn't change. Okay, and then there's isochoric. Choric is the old fashioned way for volume. So actually this, you can call it isovolumetric. I would just call it isovolumetric process. And that means, as you can guess, the volume is kept constant. I will introduce both words in case you see. I will probably use isovolumetric. So, it's easier to know what that means. And the 4th one is a little bit of an odd man out. It's called adiabatic process. Okay. What does that mean? Adiabatic is a fancy word. It's rare in physics we invent fancy words. We usually use something that's very obvious what the word means. If anyone knows the English root for that, let me know. It's cool to know. 6 words. Memorize this. No heat in, no heat out. Okay. That's an adiabatic process. That means it's perfectly isolated. Or you can say, these are equivalent, perfectly isolated. Or you can perform it very fast, very rapidly. If you perform the process very rapidly, the heat does not have time to get leaked out yet. You just suddenly squeeze something very, very quickly, right? So the heat doesn't have time to conduct. Remember how heat conducts? There's 3 ways, right? Whether it's conduct, convect, or radiate. If you do something extremely very quickly, there's no time for that. So that's adiabatic. That's at least a very good approximation, as you can know in physics. Right? It's a good approximation of adiabatic process. Can you tell what is the symbol for that? That's right. No heat in, no heat out during that process. The delta Q is 0. The next important thing you need to learn, so learn these definitions. This is a big part. The next thing you need to learn from problem solving wise is you need to master PV diagrams. This is going to be your friend for this part of the course. This is very important. Okay, put double exclamation mark. Okay, what that means is learn to draw them and learn to interpret them if you're given one. A lot of your homeworks or the additional exercise I picked is basically trying to learn how to read these graphs. So let me give you an example. In fact, I call these basically the free body diagrams of thermophysics. It's as important as the free body diagrams in mechanics and the rest of physics. So whenever you talk about forces, always the first thing you do is immediately think, I draw a free body diagram. Whenever you talk about thermodynamics, the first thing you think is, let me draw a PV diagram for it, right? So how do you do that? Let's start with isobaric. So let's say point A is over here. So PV diagram, as the name suggests, it plots the pressure and the volume of the system. So if the system has this pressure and this volume, and you increase it, keeping the pressure constant, this is basically isobaric process. This is number 2, represented in the graph. Let's put an arrow as well. And if I increase it this way, points from A to C, let's put labels, PC, that is isovolumetric. So you sometimes asked to in the questions you asked to describe, or in exams asked to describe this process. I'm going to give you a graph. What do you say for A to B? This is very simple, maybe a short answer question. 2 points or 1 point even, very simple. It's an isobaric expansion. And then if it's B to A, is a isobaric compression. And if you go this way, then you are compressing it. Look at the volume, right? If you go from A to C, that's a isovolumetric increase in pressure. If you go from C to A, that's an isovolumetric decrease in pressure. Okay. Okay, so we took care of these two. How about isothermal? How do I represent? Let me draw a new diagram for isothermal. Isothermal, okay, and adiabatic. Let's do. So far, so good. All right. So isothermal is, let's think about it. It's a little bit weird. It's a little bit more tricky because there's no T on my graph. How do I plot this? All right. So here's the clever way. So that means isothermal first. The definition is delta T is 0, or think of it as T is constant. This is the same thing, right? It doesn't change, right? But as long as we're working with ideal gas, it has to follow. It has to satisfy which law? The ideal gas law, right? So if this is constant, then we have some constant, which is NKT, this constant is, but it's the crucial bit is it's some constant divided by volume. All right, so as long as there's no leak, right? No leakage, right? The N is to stay constant. The K is definitely a constant, but don't change the number. If the gas is leaking, you need to fix your car. So how does this look? Well, this is like the basically y equals 1 over x graph, right? Look, the y is p, the x is v, like that. But the constant doesn't have to be 1. So we need to be able to think about, how to plot if the number on top is different. What does it look like? Well, let's just quickly remind ourselves the mathematics of the graph. It looks like this, right? It's an inverse graph. Basically, it has 2 sides, but we don't care about this side because P and V has to be positive. The volume cannot be negative. The pressure cannot be negative. And yeah, so this is the curve. Now, if you increase the number over here, what that does is you just push the curve diagonally upwards like this, okay? So here, the constant is larger. Here, that constant on top is smaller. Okay, so what is our constant? Our constant is the temperature. It's proportional to that temperature if N and K is constant. So a higher temperature will have the curve higher, and the lower temperature will have the curve lower. But generically, if I don't plug in any numbers, if I start off here with PA and PA and VA, it will look like this, like a 1 over, right? So it looks like this. And from A to B is a isothermal expansion. From B to A, if you go backwards, if you start from a certain pressure and volume and then you move to a smaller volume and pressure, so that corresponds to back to our piston, you're compressing it. You start from a big volume, compress it to a small volume, the pressure increase. Why does the pressure increase? Because you're keeping the temperature constant, so the pressure must increase, right? It's intuitive that way. Now these curves are called isotherms. Isotherm is curves of constant temperature. So isotherm. I'm introducing these because if I have a larger temperature, this is a larger temperature isotherm. Right? If you have a larger temperature, that constant on the right-hand side is larger. So here is higher temperature isotherms. These are lower temperature isotherms. So these are curves of constant temperature. So I could have a process that moves from here to here, right? I start off with a much higher pressure and higher volume, and then move to both a pressure and a volume that is higher than the PA and VB, right? So that's another process. But that is also an isothermal process, but it's conducted at a higher temperature. This is isothermal process conducted at a lower temperature. Now, there can be non-isothermic process. For example, what if I move from A to D? Question, what process is that? That is isothermal. isobaric, right? The pressure is constant. Now look what happens when you go from A to D. If you go from A to D, you actually move from, this is how you read graphs. You do more of that in homework. I'm going to supply the, like I say, this is the lectures are like documentaries and supplying the theories and the concept, but you'll practice a lot more how to read this graph, but I'm going to give you a quick example. What happened? You're moving between isotherms, right? If you go from A to D, you realized, because isotherms are basically these 1/x graphs, these little inverse slants graphs, right? What happens when you do this isobaric expansion? Does the temperature increase or decrease? Can you tell? The temperature is moving from a low isotherm to a high isotherm, right? So if you're just given this graph and you're not sure, what you want to do is always sketch some 1/x graphs like this first, and then you can read it and see that from A to B, this is going from a low temperature to a high temperature. Let's see if that makes sense. You are increasing the volume, keeping the pressure constant, right? So think of ideal gas law, PV equals NKT. If you keep the pressure constant and you increase the volume, temperature must increase. So the graph is a graphical representation of this equation, this ideal gas law equation. Okay, so the answer is it goes from low temperature or low isotherm to high temperature, right? It's basically a reflection. It's nothing new. There's no new concept in this lecture. I'm showing you the graph of how to interpret, how to visualize the ideal gas law. Without looking at the equation, you can look at graphs and already get your answer from this. At first, it's a little bit to get used to, but that's the point of learning new techniques. So let's talk about thermodynamic cycles now. We can talk about this. So we have the few processes. By the way, I haven't got to adiabatic yet. I will, but that is a little bit complicated. I can give you a simple example right away. Let me start with this pressure and volume. I'm not going to label the PA, PV like that. I'm just going to label the points. So what if I first go down on an isotherm, and then I move across here, and then I move back up. So the cycle ABC, or sometimes just write ABC, right? The cycle ABC, this is called a thermodynamic cycle. Okay, because you see your final point is equals to your initial point, and you can rinse and repeat and have this gas engine. This is basically, I know everything is very abstract, but think back, this graph is describing the gas here. Okay, so always have this visual. This is very mathematical, but it's actually something very physical. Okay, so you can get a question in an exam saying, can you describe this thermodynamic cycle? So what you're going to tell them is, from A to B, first of all, it's an isothermal expansion. And then from B to C is a isobaric compression. And from C to A, it's not expanding or compressing. You see the volume stays constant, but so the volume it's isovolumetric, but it's isovolumetric, just increase in pressure like that. Okay. But what we're most interested in is not what the gas do. I mean, that's cool and stuff. What is question from a chat? Why is A to B isothermal expansion? Because this is the shape of isothermal expansions. It has to be a particular shape. If I slant more, if I end up going from here to here like that, of course, or if I slant less, right, you have to have the correct slope. But assuming I drew it correctly, yeah, like that, yeah, right. We're not. It's all good and fun and games with what the gas does, but that's not what we care about. Right? We care about how much work it's going to help us. It's going to benefit us, right? Because we are, by definition, lazy, and we want to make machines that do us work. How much work does this thermodynamic cycle do for us? What do we get out of it? So question 2. So this would be a very well part A of a long question. Easy part B, that part A would be very easy, right? And then it could be asking how much work is done by or on the gas, by this machine, by this piston. Notice we are physicists. We're interested in just how the energy flows between this. How does the energy get converted from heat into work? We are not concerned about how you then connect this piston into the actual gears and nuts and bolts and wires and stuff that makes the engine work. So this is basically where we separate the work from physics analysis and engineering. So engineer takes everything they learn from here, and then they try to piece this together and stitch everything on the front end over there, and try to make this back and forth work. Physicists, we supply the theory for them. We explain to them how exactly the gases will work, how exactly it will behave, and now they can take it wherever they. Usually, physicists lose interest after that. All right. Joking aside, so now back to how much work, right? So delta W. What? So technically, we want delta W of ABC. Now, if you're lazy, you can just write that WABC, okay? How do you calculate that? So you split that into pieces. It's first you go from A to B, how much work is done, and then you add up how much work is done from B to C, and you add up how much work is done from C to A. So how do we calculate this? So first, always start with definitions, okay? You will never go wrong with definitions. So f dx, this is the general one because let's assume the f is not constant. Let's take care of a general case first. What f, what x? Remember, when you see f, always ask on what, by what, right? So let's draw our piston. So this is the system. And this is, right, the gas is going to, let's say you're burning it. So the gas is now going to be very more energetic and it's going to hit this wall harder. And it's going to exert a force. So the force is going to be by gas on the wall or on the piston, okay? And this is, as a result, going to move from A to B, and this is the delta X. Let's call it delta XAB. So it's the delta X of the box, okay? And the F is the by gas on wall, okay? Let me actually split that into two steps. Just to make it clearer. So it's the force by gas on the wall, X. We don't really know what the force is because remember we have spent the past few lectures learning P, V, and T. So let's find a way, can we find a clever way to relate force to P? Yes, because we just learned from last week's lecture that that is pressure times area, right? So there's a reason why one thing leads to another in physics. So make sure you catch up and remember all the definitions of things. Otherwise, you'll get stuck over here. Okay, so what pressure? Pressure of what? Pressure of, well, since this is by gas on wall, this must be pressure of the gas on the area of what? Area of the wall. Agree? So look how helpful the labels are. Immediately it supplies you an intuition. Now, here's a side note that if A times dx is just a small change, whereas delta x is the finite change, the complete change. So technically, you can think of it like this, right? This is the total change, and this is a small change, and this is adding up. This is how integral works. Okay, this is adding up all the small changes. So if you integrate it, right? So from initial to final, you have this situation going on. Right, so that's why delta x is the complete change and dx is a small change. Right, so it's easier to think of the complete change, right? Because we are not good at thinking about calculus infinitesimal stuff, but finite things is easier. So this is x minus xf, x minus xi, expand this out. And now if you draw this box, right, that has just expanded, this is the area of that piston, right? It has expanded from here to here. It initially, so this is xi, this is xf. A times xi is basically this volume, right? And then A times xf is basically the final volume, right? A times xf, right? So this is basically the final volume minus the initial volume, right? That's basically a delta V. Or you can think of it as the orange part over here. The orange part over here is the change in volume when the piston moves from that point. Does that make sense? It moves from A to B, right? When the piston moves from here to here, the orange part is the change in volume. Okay, so A times the change in distance, so this is the change in distance, or delta x. Right? Delta x is xf minus xi. So the A times that is basically dV, the change in volume of the box. And this is the general formula. It's very useful. I would have this memorized as well. So this, notice I call this a formula, not a definition, because it's a formula applied this is the definition. As I'm not going to draw a new box, we had that in a box earlier. But this is a formula that came from that. And in this, as long as you're solving a thermodynamic question in this chapter, feel free to directly start with this formula. You don't have to start from the definition and go through these 3 steps every time, okay? Although it's 3 steps, but you don't have to do that. So in this chapter, you can make a note in your notes that you can start. Whenever someone asks you to calculate work done, sometimes I actually will abuse the language, and I even call this the definition of work, because as you can see, if I can go from this way to this way, it's equivalent to go from this way to this way. So if I like, I can treat this as a definition and then derive this formula. But of course, this is usually our starting point. Okay. All right. So let's go calculate it, right? So let's calculate for isobaric. Now, isobaric means pressure is constant. By the way, isobars, just like isotherm, isobars are lines of constant pressure. And if you ever watch the Weather Channel on the news, if they pull out these pressure graphs, air pressure of the graphs, you see these little contour lines, right? Those are called isobars if you study geography. Yeah, so in weather forecast, climate science, geography, those lines are called isobars, just like we introduced isotherms, which is lines of constant temperature. So this is, you can, as I said, we can directly quote this formula, AB, PdV, but P is constant. This brings us to an interesting thing. You can pull that out of the integral. And as a result, if you pull that out, right, what's integrating that? If you do go through the math, it'll be VB minus VA, right? So it's just PdV, or P delta V. So if you like, you can put a box around this, because this comes up a lot as well. Okay, so this, but if you do, make sure you put a bracket and know that this is only working for isobaric process. If P is not constant, as we have seen in here, P can, in most cases, P is not constant, right? But if it is, then you can use the simple version. This is basically like f dx, right? F delta x, instead of using the full integral. It's the same steps. So this is a simple way to immediate offer. So if you know the, so if you know the pressure, final volume, and initial volume, you can calculate how much work is done. So you just look at your gas tank in your car, right? What's the smallest volume it goes and what's the largest volume, and then stick a thermometer, not thermometer, so stick a gauge inside and measure the pressure of that process, and then you'll find out how much work it actually do, or vice versa. If you want to do a certain amount of work, because remember, questions can always be flipped around. If you want to find out how much work you want to do, you want to lift something up, you want to create a machine that does that, then you can backwards engineer and calculate what pressure you need to put in here, what's the volume size, and stuff like that. Right, so that's isobaric. Let's do isovolumetric. Believe it or not, this is so simple, because if the definition is volume is constant, which means delta V is 0, right? So if you use the definition, if it goes from A to B, if the volume doesn't change, it's completely 0, right? Are you surprised? At first, maybe, but if you look at the graph of the PV graph, when you go from A to B with isovolumetric, what work have you done? You've done no work at all. The volume stays constant. If you connect your piston to a box, the box would just look at the piston like it's an idiot. It just increased the pressure. It's not going anywhere, right? So there's no work done. So isovolumetric is that. So this brings me to a neat trick. Let me use a different color. So 2 neat tricks over here immediately before I go to isothermal is, if you stare at this, remember your math, right? You realize that integral of something is the area under the curve. So this is represented by the area under a PV curve. Look at the isovolumetric process. What's the area under this curve? 0. Whereas for, let's say, isobaric, what's the area under this curve? Here. Can you calculate the area? Sure, the area is going to be PA, that's the height, times VB minus VA, right? So the height times the width. That is precisely P delta V. So the work done is actually the area under the PV curve. So this is how you read PV diagrams and read and interpret them, right? So you see, that's that. Now, is this positive or negative? it's doing positive work because the volume increased. So just use common sense. So here it's doing, so the work done by the gas is positive. Okay, by the system is positive. What's the work done on the system? Well, there's no work done on the system. The system's doing the work. But according to our rule before, one is the negative of other. So if the question is dumb enough to ask you what's the work done on the question, even though there's no work done on the question, it's on the system. It's the system is doing work, so there's only work done by the system. If it does ask you what's the work done on the system, then whatever you calculate from here, put a negative sign in front. Okay, just from that rule of one is the negative of the other, just from conservation of energy. One is the negative of the other. So in general, if I have the four isothermodynamic processes are just the four most common ones. I can have really weird random ones like this, right? But of course, we're not going to study something complicated like this. But if you do, if you need, this is the amount of work, right? The area under the graph going from one to another. You won't be shown these, but that's the principle. Okay. So that's I said two tricks. So that's the tip number 2. So tip number 1. Tip number 2, taking doing the magnitude and then the signage separately. Also this, yeah. Okay, so we can look at a cycle here. Now, if I have that, right, first, if I do this, go back to my almost triangular cycle, right, the isothermal, and then Isobaric, and then isovolumetric, right, go up there. Now, here's how you should look at this. This is the area under the curve. So that's the amount of work done by the gas, right, by the gas. So whatever value that is, right, so the work done by the gas is whatever value that is. Does the gas gain energy or lose energy when it does work, when it goes from here to here? So when it expands from here to here, it will lose energy, right? So if you expand, let me put you in a box like you are a gas particle and you try to expand that piston. Will you lose energy or gain energy? You will lose energy. But what if someone pushed the piston back on you, which won't be comfortable, but will you gain or lose energy? You'll be gaining energy when someone pushed that back on you. So another way to think about it is expansion means it loses, the system loses energy, and compression means the system gains energy. Don't memorize these, but just think through. I like to put myself in the box. It's usually a general bad thing to do in life, but in this case, it's nice. It's easy. And then think about what will happen to you. Do you gain or lose? I think otherwise there's so much plus or minus things to memorize. It's impossible. That's an uphill battle if you go that route of studying. So learn the logic of this. So the gas would lose this amount of energy, whatever the absolute value is, it'll lose. Now, but when it goes back from B to C, if it goes from B to C, what happens? Then this is the work done, right? Area under the curve from B to C. Is this work done by the gas or on the gas? Because the volume is compressing, as I just using my logic, right? That is work done on the gas, which means the gas is gaining this amount of energy. Okay, let's say AB, BC. You calculate W BC, delta W BC, take the absolute value, and then put a positive sign, right? It's always absolute value because if you use my way of doing it, you always take the larger number. Well, actually not necessary. You can take final minus initial, but whatever you do, just think through, is it positive or negative? Do the magnitude and direction just completely detached from each other. So what do we learn from this is the middle part, because it does the yellow part of work and then it gains back the green part of work. So the middle part is actually the net work that is done. So this is the net work done, okay? Net work done of our machine, okay? This is called a heat engine of our engine, okay? So you learn a new thing, put a star around this, is the net work done, because when you connect that to the wheel that I put in one of my early slides over there. If you connect that to the wheel, in the expansion phase, let's say it's actually doing this, right? It's isothermally expanding, so it pushed the wheel over there, and then it's isobarically contracting, it pulls the wheel back, and then it goes back up. It's not doing anything, but you just increase the pressure again, so you can restart the cycle. So here it's this, from C to A, you increase the pressure back so that you have a chance of restarting the cycle, right? So if you keep going over there, every cycle that the wheel goes, that's the orange part the area that is enclosed inside any graph is the net work done. So if you're given a very obscure heat engine, it says, oh, the heat engine starts here, that's the initial state, and then it first goes here, and then it goes here, and then it goes here, and then it goes here that way. What's the net work done of this heat engine? Well, if there's some magical way of finding out that volume, you won't get this type of problem, but that's the general idea. It's the area enclosed inside a thermodynamic cycle. Cycle consists of processes. Okay, cool. So let me, right, so talk about isothermal, right? We get to isothermal as well, but sometimes we're also interested in the change in energy of the gas, okay? So you not only, so overall, actually there are lots of questions you can ask. You can ask, what is the work done of a process or a cycle, a certain process or the whole cycle, right? Cycle, just break it down to process. And how about the energy of it? The internal energy over a certain process or the whole cycle. How much heat has been added in the whole either process or again a cycle, right? These are types of questions that you can ask, okay? So I again will let you, okay, I'll do one more example and then some of them I'll leave, I'll let you fill in the blanks because hopefully I've explained a lot of the background that the textbooks don't explain to you. And so it makes you reading the textbook easier. Remember, that is my goal of lecture. So I not necessarily will cover everything. The textbook is basically all the reference chapters or things that are basically part of the course that your ability tested on. But this is the purpose of this. Hopefully these explanations will basically aid your learning there. But this is actually quite, it involves some new skills. So let's talk about isothermal. Isothermal is, what's the definition? The definition is delta T is 0. Right. What is, so if I want to find a change, so if I have a isothermal process just like this, right, from A to B, what is delta EAB? Okay. So if as long as it's an ideal gas, you need two formulas from yesterday's lecture, either this and this. With these two formulas, you can conquer the world of ideal gas. If you like changes to a different color, I just save a second and not do that, or put a star next to it. These two you will want to remember, it's always applied to ideal gas. So whenever you're talking about ideal gas, keep these in the back of your head that whenever relevant, try to use them. Okay. Notice this is NKT over here. That's the second one comes from kinetic theory. So this comes from the microscopic analysis. This comes from the macroscopic analysis, right? This is also PV, right? So you can, this is also maybe, if you like, you can also put this inside the box. Okay. Yeah, so over here, let's see. So I'm concerned about 3/2 NKT because I know I want to find E, right? So I have two formulas I can use. So today, the key formula is this. And from last lecture, so with these two boxes, you have basically the key things you need in the course. Of course, you need to know how to use them. So which one should I use to find E? Well, let's look at this one. Do I know delta Q? No. Do I know delta W? No. So this is not useful. So let's use this one, right? Or this one. Since I'm given delta T is 0, it looks like this is more promising. That's why I know I will use this one over here, right? So you plug in E is this. You plug this in here. Now, 3/2 doesn't change. N, as soon as it doesn't leak, it doesn't change. K is a constant. So those can be pulled out of the change. What is delta T? Isothermal, by definition, is 0. So the change in internal energy is 0. Of course it is, because if you think about it now, it's a dumb question, because temperature is a measure of internal energy. So if your temperature doesn't change, internal energy, of course, doesn't change. But this is the proof over here, the algebraic proof, so you understand it once and for all. So now, the next question of the open response question in an exam may ask, well, what is the delta Q and what is the delta W of this process, right, for this isothermal process from A to B? Well, from the first law of thermodynamics, it's called the first law. It's so fundamental because it's a conservation of energy, as we mentioned, which means, so we have delta E equals first, another tip in exam, always, let me change the color to emphasize this tip, always quote the original formula before you start plugging in things. So the TA or whoever's grading it, know what you're plugging in. If you immediately just plug in numbers without the blue line, and then you just write the next line saying 3 equals to 5 plus 7, right? Or that doesn't make sense, but you get a point. Then where does these numbers come from? It's impossible to grade to see if you understand it or not. So your goal to get the maximum pressure credit is to show that you understand things. As a result, quote this word for word first, then apply it. That's my tip for doing exams well, to showing understanding well. So first, this is 0. So that means delta Q is negative of delta W. Okay? I still don't know what that is, but let's find out. But we know that if I know W, I know Q, right? If I know Q, I know W. So that's for isothermal. So how do we, maybe I should add one more, is this formula, right? AB, AB. This is the 2 things we learned today. So delta W, excuse me. So if I'm asking delta W, is it easier to calculate this or this? It's easy to calculate this because I have a formula for that. So let's plug that in. AB first, again, like my suggestion, copy that word for word first, the definition. And then now you think, is P a constant? No. If you look at the isotherm over here, the P is not constant, right? It changes, it decreases. So what do we know? Well, there's another ideal gas law, right? You see, ideal gas law tells us P is equal to NKT over V. Maybe this is helpful. Let's see. So let's plug that in. And now I see a bunch of constants I can pull out. Why can I pull out the T? Because by definition, isothermal. It allowed me to do that. And if you don't know what this integral is, brush up on this. Integrate of 1 over the V is log V. This is the special case that is a little bit awkward. Most of the time, you just increase the power by 1. But when it's 1 over V, if you increase the power by 1, this is 0. But then you need to divide by the new power. There's something going wrong. So that the power rule of integration doesn't work for this, for a special case. And the correct answer, if you do a more sophisticated mathematical analysis, it is log V. So just memorize this, this special case. And now you plug in the numbers because it's definite integral. So log VB minus log VA. Just by the rules of logs, you can combine that in one fraction inside one log, right? So let me put a box around this. This is the formula for isothermal. Now, should you memorize this? No, do not memorize, even though I'm putting it in a box because it will come up a lot of times. Derive this every time. Okay. This is what I call low-level formulas and not a high-level formula. Low-level means that you start from some fundamental things and you derive your way down to something lower level. Okay. No one, yes, for this course you could memorize this, but after that, no one remembers this. If I ask any of my physics colleagues who are doing research every day, they don't, and I ask them to quote this formula, they will never be able to pull this out of their brains, but they will be able to pull this out. And if you know how to do this, then this is as good as this, because you, in just within 30 seconds or less, you should be able to get these results from this. Okay. And okay, so just to summarize, this was negative of this, as we learned from the first law, right? So again, don't memorize. If you want to memorize all of these, you know what, you can try. You can go ahead. Everything I say is just a suggestion. So your brain would probably explode from this chapter. People sometimes find this chapter difficult because there's lots of formula, but I want to tell them there's only 4. Right? There's technically this one comes from just there. So if you know these 4, you can conquer this chapter. And I do not encourage memorizing all these subsidiary ones, even though I'm putting in a box, because this neatly summarize what all the facts about isothermals. Okay, so I want to tip it here. Don't memorize, learn to derive. So I will not fill in all the gaps of this table, but this is something you can do as a post-lecture exercise. And this is actually very relevant. So this is not extra stuff, but it's actually relevant to the class. So write down all 4 of these processes. And ask yourself, first, can you fill in this table, the definition? And then ask, what's the change in energy? What's the change in heat? What's the change in work? So I'll fill in a few for you, and you can read the book and understand how to fill in the rest. Right? So the definitions here is simple. Okay, memorize that. We talked about isothermal in depth, so let me fill in this. Isothermal means energy, internal energy is 0 as well. And delta Q is negative of delta W, which is negative of NKT log B minus over log A. So as you can see, although we're filling in this table as an exercise, you will have like 16 different equations to memorize if you want to memorize every one of them instead of 4. So learn to derive this is my advice. Okay? You will have enough, the exams are going to be designed so that you have enough time to derive this on the spot. Okay. And so yeah, go in and you can go and fill all these in. Actually, we did isobaric, right? This is actually pressure is constant, which means the W takes a very simple form. And we also talked about this one. Remember what is isovolumetric? What is the work done when it just goes up and down? Remember, it's 0. Okay. All right, so the rest is an exercise. Or I might not have covered some things, but if you with this background, when you read the book, it'll be very easy. So I haven't addressed adiabatic yet, as you can see. So recall, it means no heat in, no heat out. Okay. By the way, this one is performed rapidly, right? Isothermal, on the other hand, is performed slowly. So sometimes the questions, I hope I won't have too much of those type of questions, but sometimes they don't explicitly tell you the process is isothermal. They just say, or adiabatic, they just say this process is performed very quickly, and you need to identify that keyword of quickly or rapidly, right? That means adiabatic. And sometimes they'll say it's performed slowly. That means isothermal, because if you do it very slowly, it has plenty of time to conduct. It's the opposite of adiabatic, because you have plenty of time to conduct with the outside temperature, whether it's room temperature or not. And you can, if you imagine compressing it very, very slowly, it won't heat up as much as if you suddenly push it in. If any one of you pump your bike before, if you push it in and out very, very rapidly, the gas will heat up. But if you do it very, very slowly, the gas will not heat up, right? So performing extremely slowly is a way to achieve isothermal processes. So what can we say about this? Well, this one, by definition, delta Q0 from first law, that immediately tells us something, that, right, delta E is actually the same as delta W. So you can choose either or to directly calculate that. So you can, there's 2 ways to actually calculate this, delta E or delta W, because you can actually use delta E is delta 3/2 NKT. Now this time you can't pull the T out. Sorry, you can pull everything out, but not, yeah. So, but the T changes, it's not isothermal, right? So what you need, this would basically translate into this. Okay, so if you know the final initial temperature, you can calculate the delta E. But a lot of times you don't know that, because usually you're given PV graphs. So you only know PVs, you don't know T. Although you can use the ideal gas law to then find the T, a more efficient way is use the ideal gas law from the get-go. Like this. You can pull the 2/3 out, oh, sorry, 3/2 out, and then you can do P final, V final, minus P initial, V initial. So you're usually maybe given 3 out of 4 of these. So if you're asked this, now you can use the ideal gas law, right? Because if you remember, PV over T is constant. So you can use the ideal gas law. If you know, you can compare 2 points between that, and you can find out what that is, and then you can find out what that is. Okay. If that doesn't work, for example, if there's more than 2 unknowns in this equation, you might consider using the other approach. But if you do the other approach, you need 1 more equation to substitute what P is. And this one, unfortunately, it's out of our scope of the syllabus to prove that this is the formula that works for adiabatic. So this would actually be something else you want to put over here, and maybe next to the definition, you want to put this. It's not a definition, but it's something that technically in a lecture I should prove it, but it's the mathematics is a little bit beyond. The textbook has the proof, but you don't have to worry about that derivation. What is the gamma? The gamma, if it's a monatomic gas, the gamma is 5/3. If it's a diatomic gas, it's 7/5. Okay. So this is around 1.666, 1.67, right? This is about 1.4, like that. Okay. So that's the number that depends on the gas. So it depends on the gas. What monatomic means, if it's like a hydrogen gas, you have a single atom. And if diatomic gas is like oxygen or helium or nitrogen, like N2O2, if it's a diatomic, there's two atoms per molecule, per particle, right? We use the word, then that is the correct number. It's not the big difference, but this is you need to derive it in a more higher level way. Once you do that, you can plug this in here and get a formula for that. I will do it very quickly due to time, but you can get the idea. So it's a constant over V gamma. Okay. So maybe I use a new slide to, where was I? Right, so find the process over here, AB, PdV. So we have this formula like this for adiabatic. So that means P is a constant times V. You can put that to the other side. So we can write that as constant times V minus gamma, right? So that is appropriate for adiabatic. Constant can be pulled out, AB. To do an integral, what you do is you raise that by 1 power and you divide that by the new power. And then you put in the limits. Okay? This is just a number, right? Either 1.6 or 1.4. You can pull it out of the brackets. Let me write as 1 minus gamma for convenience. And then now you plug in B and A. So it's VB minus VA. I'll write this 1 minus gamma instead of minus gamma plus 1. Just looks a little bit better. So that's this. Now you might wonder, okay, what is this hanging constant over here? Well, usually, remember, you're going from initial to final, right? So you have a process that moves something like this. So if this is constant, what that tells you is P1 V1 gamma is P, let's call it PA, because I was using PA and B, PB VB gamma. Remember, I told you this technique of seeing equations of something equal constant will keep coming up in physics every now and then. So here it comes up again. So what you do is you pick 2 points and compare, just like Bernoulli's equation, right? Like this. So this constant means that during this process, it's constant over the process, right? Throughout the process, the adiabatic process. So you can either use this or this. So let me use initial and final. Maybe I'll use those notation. So you can either use, the constant can be initial. So sorry, let A equals initial, B equals final. I want to be a little bit more instructive. When you look at this, you can immediately tell what it means. Right? Or you can use this. Which version should you use? Like in front of here? Well, depends on what you're given. So depends if you're given the initial, usually you're given an initial and predict the final state. Okay? That's how predictions work. But sometimes, problems can flip it around and ask you the other. Okay. So again, definitely don't commit this to memory for your own sanity's sake. This derivation, you do, it's a little bit tough, but try to learn it. I would say it won't be directly tested on this. And very likely, if you need to use this, it will probably be a formula that is actually given on the first page of the cover page of whatever test or exam it is. But have tests aside, to try to learn this, because this is probably one of the most difficult, one of the top three most difficult derivations in the class. So if you can do this, you train yourself in advance before we head on to more other stuff, other integrals later on in the course. This is a good warm up to get your muscle working, right? Get your recap. So learn this, how to derive this. Certainly don't memorize this. If you ever need, we will give you this. Usually the general rule will be, if any formulas that is more than 3 or 4 variables put together in a non-trivial way, we will give you that. But if it's a formula that only have 3 variables, like pressure is force per unit area, we'll probably not give you this. This is the definitions you do need to know, right? Or density, right? Things like that. In the end, I might, but I don't want to say that right away. So in the end, there's a good chance I'd be nice and just put those and stuff, but don't rely on them. That's what I'm saying. And just for learning purpose, those should be memorized. That's the point. For exam purpose, I know exam is a little bit different because my philosophy is in exam you're under stress and pressure like that. So sometimes even if you remember it, you might forget. So we'll put that there for reference. So it's for checking purpose. Usually that is the philosophy for putting the formulas there. Okay, we'll talk more about exams logistics in the future, but for now, that's the idea. Okay. Finally, I drew the graph. I didn't explain for adiabatic why does it look this way. So if you think about it, let's put a reference. This is isothermal, let's say. Isothermal is PV equals NKT. So this is constant if this is isothermal. But adiabatic follows a different rule. Well, it follows this, but this is not a constant. But if you do PV gamma, this is a constant, right? So let's write for isothermal, PV is a constant for isothermal. for adiabatic, PV gamma is a constant. So what's in one case you have P is inversely proportional to V. In the other case, you have P is inversely proportional to V gamma. The gamma is something, it's either 1.6 or 1.4, right? It's either 5/3 or 7/5. So which one decreases more? If this is the initial point, does the adiabatic end up at a lower pressure, or does it end up at a higher pressure or does it even go up, adiabatic expansions? Well, first of all, it has to be inversely proportional, so it cannot go up, otherwise it will be proportional. It will be some sort of positive relationship. The fact that it's on the bottom, it has to go down. So the question is, does it go above? Does the pressure decrease less than isothermal, or does the pressure decrease more than isothermal with the same expansion? Now you look over here and you see if I have the same V, this is a larger number. This is V to the power of 1. That's V to the power of 1 point something. So the P would decrease more. So if V increase a certain amount, P would decrease more for adiabatic. So this is how adiabatic process looks. Okay. So this is adiabatic expansion. The other way around is adiabatic compression. Okay. So it's a steeper curve like this. Okay. So now, once we understand the 4 processes, we can build a heat engine. Okay. Heat pumps and refrigerators. If anyone's following, the reference chapters here is 20.2 to 20.4. So to build a heat engine or a heat pump or something, so to actually build an internal combustion engine, to build a car engine like that, you need 2 criteria, 2 features. Number 1, you need it to be a cycle. Right? You can't just have a process. Imagine that wheel, right? If the gas expands, it makes the wheel go forward. If it doesn't go backwards, you don't have an engine. You just push it once and for all. And the second thing is you need 2 reservoirs. So you need a hot reservoir, a hot temperature reservoir, and a cold temperature reservoir. Okay, let me explain what that means. So for a heat engine, these are the key. Here is the key diagrams you want to learn for this part. You draw the 2 reservoirs and then you draw the engine. Okay, so first, this is the diagram. You have a hot reservoir, a cold reservoir. You put your engine in the middle, and the heat will flow from here to here to here. So remember, heat will always flow from hot to cold. So if you have a cold area and a hot area, let's say you have a ice over here, you have a burning metal over here. Before you just touch them together in the middle, you put some sort of pedal, some sort of engine, basically put a box of gas and allow the heat to go from one side to another. It goes to the gas would expand and then it will do work, it will push something else, right? So that's how you want to build it up. This is the very schematic idea, is that the heat will flow, certain amount of heat will flow from here to here, and certain amount of heat will flow from here to here. So we'll call it delta Q hot, delta Q cold, and in that process, it will do work. Okay, so in that process, this will do work as long as the heat flow. Okay, from the second law of thermodynamics, we talked about heat will always flow from hot to cold reservoirs. So this is a very schematic, look how simple physics is. We don't care about the nuts and bolts in engineering and building the engine. You might think in order to build a car engine, it will be very tough to do, but this is all we care. This is a heat engine to us, okay? And this is a principle because we're concerned about how the energy flows between things. And we can construct this formula from just a conservation of energy, right? If you add up, this must equal to this plus this. Everything is energy. So however energy flows into the engine, some of the energy would get transformed into work, some of the energy would get just flow out of the engine. That's why your car has an exhaust pipe. It's flowing the energy, that's this part, it's flowing the energy out. It's taking the energy in, so there's a explosion tank going on, the combustion tank. It's making things very hot inside the car engine, right? And there's a tank that make it very hot. The heat will flow into the pistons. If you know about cars, you hear them talk about pistons. TH and TC stands for hot and cold, the hot temperature and the cold temperature reservoir. And the pistons are basically the engine, and the heat flowing from there will make the car, you connect that like I drew in the first slide, right, to a wheel. And then if you have the cycle, if you have the reservoirs and if you have a cycle, now you can actually make the car move. right? So, right, so this is how the energy works, right? And it's very obvious from the diagram. Again, my advice, you can probably know what I'm going to say. Don't memorize this. Learn to draw the diagram, okay? So this is actually called the equation of a heat engine. But I wouldn't memorize this because, as I'm going to show you on the right-hand side of my page, there is a very confusing one that is very similar. If you memorize it, it will be very difficult to learn which one is which. Don't memorize, learn to draw the diagram. Draw and derive from the diagram. Okay, that's the study tip over there. Now, like I say, on the right-hand side, I'll draw something very similar because I'll draw it for a heat pump. A heat pump and a refrigerator is actually the exact same theory. Think of heat pump as a radiator. In a cold winter day, you pump the heat into your room. That's a heat pump. You make something hotter. A refrigerator is standing on the other side of the heat pump. You're taking away the heat from it. So a heat pump, either you pump the heat into the room, right? Or you're extracting heat away from the box, the refrigerator box. So it's actually the same theory. It's just which side you're interested in. So this is the same. So same, you have a engine here. This time it's a pump, right? You have two reservoirs. You have a hot and a cold reservoir. But this time you're not interested in doing work. This time you're actually interested in taking the heat and move it from one side to the other. So what the diagram is drawn is this. You put in work to pull the heat from the cold to the hot, because it naturally will not go this way. You need to insert some work. It will pull some of the heat from the cold reservoir to the hot reservoir, all right? And now, this looks very abstract, I know. I'll draw an actual refrigerator on the next page, so you'll see concretely what this abstract diagram would look like. But let me write out the conservation of energy first. So you see that if I take QC plus W, it will equal to QH, right? So look how similar these two equations are. This is the equation for a heat pump. Actually, they're identical, sorry. I never memorized them. That's why I learned how to draw the diagram and then try to derive from it. Yeah, so energy is conserved. It's always conserved. All right, yeah. So let me, but learn to derive it. I think that is just a general advice. I'm sure you guys understand. You're very good students. So let me introduce one more jargon. It's the efficiency. That's why a lot of things we care about real life now, right? So we want to know how efficient things are. And this is the definition of efficiency. It's useful work out of total input. Okay. Now, this sounds very subjective, and it is. This is the definition for efficiency in general, but efficiency of a heat engine, for example, this is no longer definition, I'm just applying the formula. What is the useful work in this case? Well, the useful work is delta W. So we put delta W on top. And what is the input in this case? Right? So how much useful work you get out of a total input? You're inputting this amount of heat, right? So when you go to the gas station and fill up your tank, it's actually, this is what the gas is producing. This is what the petrol is producing. And this is the part you care. The exhaust is the part that has to go out because you need it to flow, but you don't really care about this. Actually, we should, because this contributes to heating up our Earth, and this is basically the root of global warming. So we should care, but unfortunately, on the industrial side, this is not useful. Okay, so this is the useful divided by input. Okay, so if you are interested in climate science and helping to save the Earth, this is a very useful formula because you can calculate how much heat is actually. I mean, I'm all for taking heat and doing work. If I can do this 100%, great. But as we will learn next week, there's the third law of thermodynamics that says it is impossible to any engine to be 100%. There's a maximum theoretical limit to any heat engines that you cannot be 100% transformed to this. As a result, there's always exhaust coming out when you make engines. So it will always harm the Earth in some way. So if you're interested to know how much it does and how to make it more efficient, even if not eliminate it, this is a useful formula to work around, to use, right? So work is delta H minus delta C from what I wrote over here, right? And divide by QH, you can simplify this, and this looks like, let me zoom this in. This is 1 minus delta QC over QH. So if you like, you can memorize this, but again, this is better learned for heat engine than memorized. Whereas for the efficiency of this, it depends, okay? So it depends whether you're talking about the heat pump or the refrigerator. So let's actually draw a refrigerator. That's my refrigerator. And what you do is you put a pump over here, okay? So every refrigerator, for free, they will include a pump. So let me take my diagram and rotate it 90 degrees. You'll see it's exactly the same diagram. You will take certain amount of heat that will go into the pump, and the pump, it will exhaust certain amount of heat. And here you want to do some work in order to pull it from the cold reservoir to the hot reservoir. So you pull this amount, right, and exhaust this amount. You see how this abstract diagram suddenly becomes very intuitive. This, according to physicists, this is a refrigerator. Okay, so you have a cold reservoir, which is inside, and a hot reservoir, which is the environment. Sadly, the environment, inside the fridge. Okay. All right. So yeah. So this is the fridge is the cold reservoir. The environment is the warm or hot reservoir. Okay. Yeah, by the way, so you can analyze this and look at QH. What is QH? Just look at the diagram. You'll see that it's this plus this, right? So every time you do 1 unit of work, let's do 1 joules of work, and you extract, I don't know, let's say you can extract 10 joules of heat out of it. That is a very efficient refrigerator. I'm just making up numbers here. You actually exhaust out 11 joules of heat out to the environment. Look how sad that is. You pull out 10 joules, but you exhaust out 11 joules. So refrigerators are actually extremely detrimental to the environment. I mean, I'm all sure, ideally, let's not exhaust anything to the environment, but even if I have to, it would be good if I pull out 1 unit and I exhaust 1 unit, right? But unfortunately, if I pull out 1 unit and I will exhaust more than 1 unit because I need to, the pump is actually doing work there. So lesson number 1 is, so there's a, let me put this in brackets, not an official lesson, but never leave the fridge door open. Never open a fridge door for cooling. You know, in summer, if you live in the desert, it would feel like, oh, that's great. I want cold air. You open the door and there's a breeze of cold air. But what you do not realize is, oh, nice hashtag. What they don't realize is, as soon as you close the fridge, the house is 11 joules warmer. you feel this, right? You open the door, you feel whatever's cold inside. You get a dose of cold reservoir stuff, but then the room gets warmer. So it actually makes the room hotter. Okay, I'm not talking about politics. I'm talking about physics. Okay, okay. So, and where does that come from? It's from this. All right, let's talk about heat pump. Now, let's say we had this opposite scenario. It's snowing outside. It's extremely cold. You're freezing inside. Now what you do is you put a heat pump over here. And now you can realize you draw some amount of heat. This time, this is the cold reservoir. And this is the hot reservoir. Because you're drawing the heat from the cold and inside, hopefully you'll get this amount of heat inside, right? And you need to do work. So you plug that into a power line, some power station, it has a heat engine there. So the heat engine does the work, it sends it over, and then you use that work to draw the heat from outside. As long as outside is not absolute zero, there's always internal energy outside, right? There's always internal energy. Even if it's colder than inside, there's always internal energy, which you can extract from. So that's what a heat pump is, extracting it from inside to outside. Sorry, from outside to inside in this case. So if you look at the efficiency of these things, and sometimes it's called coefficient of performance, just read the relevant chapter that I quoted, 20.2 to 20.4. I'll save some time and not write out everything in detail, all the abbreviations. So it's useful work over input. So for a fridge, what is the useful part? Do you care about this? Remember, heat engine, we care about this, right? We care about work. But for fridge, no, we care about how much heat we can pull out. So it's a subjective thing, efficiency, it's a subjective thing. It depends on which way we care about. The physics of a heat pump and a radiator and a refrigerator is exactly the same, the physics, as you can see. But one, you care about the other side, one, you care about the other side. So the useful part is this for a fridge over the input. Okay. And usually we measure the cold and hot temperature. So usually we want to eliminate away the W. Let me stare. I never remember the formula, so I will stare at that and then remember and try to figure out what W is. So W is, so QC plus W is QH. So W must be QH minus QC. So if you write that out, QH minus QC. So learn how to do this, then you don't have to memorize it. Right? That's for a fridge. For a heat pump or radiator, the efficiency or coefficient of performance, how well it performs. This time, what is useful is the inside, is how much heat you generate inside per unit work you put in. So this time you see the denominator is the same because it's the same physics. You can check that, but the useful part, the numerator, is different. All right, so this is the end of today. Let me tell, good. So you can read more details. Do supply yourself with the complete understanding in these chapters. And let me tell you what we'll do in the next lecture, which is not part of the test, but to let you know where we're going in 2 sentences, is in the next lecture, we'll talk about the theoretical perfect heat engine. What's the best heat engine, most efficient one we can construct out of this? It's the perfect heat engine. By perfect, it means it's not 100%, but it's the maximum efficiency, maximum theoretical. So this is next time. I'm going to make this a little bit messy, but the maximum theoretical efficiency limit. Turns out, just a quick teaser, is it's actually a cycle that looks like this. This is actually the best cycle you can do. And this is called the Carnot cycle. We'll learn what that means next time. Right? An engine made out of this is called the Carnot engine. Some French guy figured out all the mathematics and the physics of this. Right? So what it actually does is you do it's a combination of isothermal and adiabatic processes, and then you compress it through this. That's why we actually learn about isothermal and adiabatic, because it's used to make the perfect heat engine. And basically a lot of startups and a lot of industries is trying to improve our energy condition in our current world. Is studying a lot about this particular cycle, and now you know the physics and the theory behind this. Okay, one key formula that comes out of this is this ratio is equals to the temperature ratio of the reservoirs. I'm not sure if I have I don't think I have a homework on this because this is next week, but just in case, I think I don't, I'm 99% sure that will be used. Okay, so a machine with a thermodynamic cycle that produces net work done is a heat engine, and a machine that produces negative work done is a heat pump. So we'll talk about this perfect engine next week, and that's it. Any questions? All right, if not, good luck, and I'll see you next week. Thank you for staying, and have a nice day.